Alright, we're going to dive into Chapter 5 and learn some exponent rules. I'll tell you the first part of Chapter 5, this 5.1, is probably the trickiest section because there are multiple rules at times that you can apply, or multiple ways you can think of a problem. Even though either of them are correct, you might think of one rather than the other, or you might see it differently, but you are still likely correct. The hard part there is learning to see the rules as interchangeable. But let's learn the rules and let's look at the examples and see what we can do. So for the product rule, we have that if I have a to some power times a to some other power, then that's simply a to both of those powers added together. An example of this would again be if I had 3 squared times 3 to the 5th, then I would now have 3 to the 7th. And we won't do this for all the rules, but for an example of that, why is that true? So just remember that 3 squared is really 3 times 3, and we're multiplying by, so maybe I'll just draw a bigger multiplication dot to represent that. But really the size there is not meaning anything different mathematically. So 3 to the 5th would be represented like this. And so really what we've done is we've taken 2 3's multiplying together and 5 3's multiplying together and just stuck a multiplication dot in between. So really this is now just one big line of 7 3's repeated multiplications. So that's the addition rule, and that's why it's occurring behind the scenes. The next one, we won't necessarily explain this one, but anything to the 0 power is going to be 1. If we want to be technical, we'll say where a is not equal to 0. We should technically throw that in there, because 0 to 0 is actually something you'll have to take calculus to explore. But really, anything to the 0 power, so 5 to the 0 is 1. Careful, negative 7 to the 0 is 1. Pi to the 0, that's 1. Now the thing I'm pointing out here is notice that in parentheses, that entire negative number was being raised to the 0. Just as an extra example, if I had 7 or negative 7 to the 0 without parentheses, that would actually be negative 1, because the idea there is that only the exponent of 0 is on 7, or rather 7 is the only thing with the exponent. There's a negative out front that doesn't have an exponent, so the negative tags along. The 7 to the 0 did become 1, but the negative out front did not. That's different from this example where the negative is included, so now that negative number to the 0 power ended up being positive 1 in this case. So notice that the parentheses will matter. Or in other words, if you see the problem start with parentheses, make sure you type it into your calculator with parentheses as well. Alright, let's keep on going. Quotient rule. So if I have a to the n divided by a to the m, then I have a to the n, well, I guess I can fix it like this, to the n minus m. So rule 1 and rule 3, they don't really have numbers, but the product rule and quotient rule are actually really related, and that should kind of make sense. When we're multiplying, we're adding. When we're dividing, we're subtracting. Why should that make sense? Because, well, think about the order we learned our basic math operations. We first learned to add, and then we learned its opposite, subtraction. Then we learned multiplication and its opposite, division. So notice that like the first of the two things we learned, addition and multiplication of the pairs of opposite operations, they go together. And then their inverses, subtracting and dividing, they go together. So that might be a way to remember it. The other thing to do or to notice is that this is technically ending in the numerator. This is saying when you do this division, whatever this answer comes out to, if you just want to subtract those numbers in order, top minus bottom, you can do that, but make sure the a, the base as we call it, is in the numerator as a final answer. So if I add a to the 3 over a to the 5, then I have a to the negative 2. Or if I have 3 to the 8th over 3 to the 5th, then I now have 3 cubed. Alright, just to explain this one, I guess we are doing some extra explaining, but oh man, I shouldn't have chosen to the 8th. But if I add 3 to the 8th, then I've got 8 3's multiplying together. And on the bottom, if I had 3 to the 5th, I'd have 1, 2, 3, 5 multiplied together. And the idea is multiplication, like when we write PEMDAS, the M and the D and the A and the S, those can be interchanged in their orders. You can do multiplication and division if they're going to occur next to one another, so to speak. You can do that order in any way you want. And so what we are going to do here is we're going to divide early. We're not going to actually calculate what on earth 3 to the 8th is, because we're going to notice that there are 1, 2, 3, 4, 5 shared pairs. Or in other words, we can kind of look at that. 8 minus 5 is 3. Or in other words, 5 of them had a match and 3 were left over. Where were the 3 left over? In the numerator. Similarly, if we work to this one out, there would be 3 A's on top and 5 A's on bottom. And so there would be 2 A's left, but on the bottom. But notice that we do our subtraction directly and we write our answer in the numerator. But here's the next rule, the negative exponent rule. If I have a to the negative n, I'm allowed to refer to that as 1 over a to the positive n. Maybe the short way of saying this is you can change the sign of an exponent if you move the base over the fraction bar. That's a different way of saying it, but it's the same thing. So if I have an a to a negative exponent, and it was on my numerator, and it is because I didn't see a fraction, I can transfer that a to the n to the denominator, and now the negative is gone. And that's actually a continuation of this rule right here. See, because a to the negative 2 is 1 over a squared. Or in other words, let's do this other problem then. If I had a times a times a over a to the 5th, 5a's multiplying. Again, a could be 7 or 23 or whatever you want. Those cancel out, and look what there is. There's 2 left on the bottom. And so this is, again, just saying, hey, this rule, and this is where the options come in that I said could be confusing, is if I have 3 and 5 on the bottom, I could subtract and just say that's negative 2. But why is it negative 2? Because we're saying there are 2 left over from the subtraction, but they're on the bottom. If I don't want to write them on the bottom, I could move them up to the numerator and just call them negative. It was positive on the bottom, now it's negative in the numerator. So hopefully that helps, but that's probably going to be our most confusing thing, is remembering what a negative exponent is. It means there's a positive version of it on the bottom, and it's however you choose to write it. All right, power to power. If I have a to the n to the m, then those two end up multiplying. This is frequently confused with the rule on top, so just be careful. When it's power to power, that's when you multiply. If the bases are multiplying, your exponents are adding. So just be careful of that. Just for a quick example, if I had 2 cubed to the 5th, then I would now have 2 to the 15th. Why is that? Because remember what 2 cubed to the 5th means. It means you've got 2 cubed times 2 cubed times 2 cubed times 2 cubed. Goodness, times 2 cubed. And if you remember what cubed means, it means there's 3 2's multiplying together, 3 2's multiplying together. So ultimately, this is just one giant line of 15 2's multiplying together. That's why it ends up working out. All right, finally, the quotient of a negative power. So if I have a over b to the negative n, then that's the same as b over a to the positive n. All right. So if I had something like 2/3 cubed, negative cubed, then that's really 3 over 2 positive cubed. And just to work that out, that would be 27 over 8, because that's what 3 cubed is, and that's what 2 cubed is. And we write them where they came from in the numerator and denominator. All right, so this rule, just to say, is technically just this rule right here. It's just, if you don't see a fraction, there's an invisible 1. Well, now the 1's on top and the a is on the bottom. Same idea, it's this same rule right here. It's just your fraction actually had a denominator in it. So really, those two are the same rule, but we kind of just see them differently as they come up in problems, so we write them down separately. Okay, with all that being said, we've done the heavy lifting. At this point, again, this is more so your guide to the notes after, or just an assistance. So we're going to go through these examples fairly quickly, but still hopefully explain the process along the way. So we've got two things multiplying here. 3 times 4 is 12, and a squared times a to the 6th would be a to the 8th, because after all, those are multiplying, so the exponents are adding. In the next example, we're doing the same thing. Negative 4 times negative 2 is positive 8. Now, I'm at first going to write x to the 0, because that's what I get from my combining. I have x squared times an x to the negative 2. That means technically those exponents are adding, since the bases were multiplying. But what that also means is they're combining as is another way of saying that. And so because of that, I have 8 times 1, and I just have 8, because remember, anything to the 0 is 1. Alright. Up next, we've got a exponent on some exponents. So if we work that out, that's going to be 16. It's going to be x to the 6th. That's going to be y to the 10th. And we need to be careful about this rule, and we'll need to come back to this later on in the notes when we get to like 5.3. But for now, we're just going to say that exponent of 2 applies to each one of these parts of this single term. Maybe that's what we'll say. And so as this squared applies to each part of the single term, the 4 does get squared, and then we apply our power to power and our power to power rule twice. All right, let's keep on going. 2 cubed. This is a single term again, so we're in a special scenario here. 2 cubed is 8. X to the negative 5th to the 3rd is going to, again, multiply and make negative 15. Y to the 4th to the 3rd is going to make y to the 12th. Now this is technically correct, but your homework may say, please write your answer using positive exponents only. And so that would be your final answer if they require that. Now all I'm doing here is after I'm using my power to power rule, essentially, I'm using my negative exponent rule and saying, oh, in x to the negative 15th, that's currently in the numerator because I don't see a fraction, that can move to the denominator and now be to the positive 15th using my negative exponent rule. Everything else stayed in place, but just that x to the 15th, just the base with that negative exponent transferred to the bottom. All right, up next we've got some division. So 8 divided by 2 is 4. And 5 minus 2 is 3. All right, because we're doing that division rule right there. And we're just doing 5 minus 2. We're saying we were subtracting those, and so our answer ends up in the numerator. At this point, we're not necessarily using the negative exponent rule yet. All right, number 6 is where we start to have some choice about how you want to see this. Here's how I'm going to see this. I'm going to see this as subtraction. Now there are options. In fact, I'm not even going to write that, but just know that the way I'm approaching this is I'm assuming that these are subtracting. So 6 divided by 3 is 2. We're going to do the division with the coefficients. Now 7 minus negative 1 would actually double negate and become positive 8. And then the y to the 5th will just tag along. So I'm still just using that division rule, or that quotient rule rather, that it's 7 divided by, or 7 minus negative 1 in my exponents, which would actually then become positive because I said minus negative. That double negates. Now we're adding. Now the other way to think about that is this. We get the 2, we have our x to the 7th, and we transfer that x to the 1st to the numerator because it was negative. Right? That's one way of seeing that as well. And then what happens when x to the 7 multiplies to x to the 1st? Well, those would add and still give you 8. So do you want to see it as 7 minus negative 1? Yes. Or do you want to transfer that negative exponent to the numerator and then do addition because they're now multiplying? Also yes. So again, the choice can make things a little confusing. But there we go. All right, let's keep on going. Now, we have some division here, but technically, because it's all multiplication and division, we can still just apply this exponent of 2 to everything, and we'll get 9. Power to power, 2 times 2 is 4, and 2 squared is 4. All right, so we're done. Up next, for number 8, there's 2 ways of going about this. I'm going to go ahead and do this. I'm going to say that this is 1 over all of that to the positive third power. So I'm noticing a negative exponent, and I'm already saying, why don't I just transfer that to the bottom? And now that whole thing is on the bottom, and so let's work that out. That would be 1 over 27. That's what 3 cubed is. You can go ahead and Google, where is my cube button on my calculator. That'd be the best thing to do there. But there is a button that exists on your calculator somewhere. And in fact, maybe I'll pull up in what we call an emulator in a little bit to show you that. Alright, so not too bad. We're just dealing with the negative exponent, and then we're still just doing that power to power rule, essentially, as we work. Alright, up next, we've got more exponents to deal with. I think because there's already stuff on the bottom, I'm going to not do what I did in the last problem, because again, you have choice, technically. I'm going to use this power to power rule and work this numerator out. So first I'm going to have 2 to the negative 2, because that's 1 times negative 2. I'm now going to have r to the positive 2, because negative 1 and negative 2 just multiply together. I now have s to the negative 4th, and because t to the 0 is 1, t to the 0 times negative 2 is still t to the 0, so that's still just 1. So I'm writing it there, but essentially what I'm trying to communicate is I don't need to write that anymore. Okay, what I'm going to do next is, we've got some space. Number 11 won't take that much space. Draw a little line there. All right, up next, here's what I'm going to do. I'm going to move my negative exponents. So I now have an r squared. I now have a 2 squared times a 2 times an r times an s times an s to the 4th. Alright, to me that's how I see it. The 2rs that was on the bottom is still there, and I'm just moving that 2 to the negative 2 down to the bottom and making it positive, moving that s to the negative 4th to the bottom and making it positive. From there, there's still 2 more steps here. I'm now going to clean up my denominator. That'll be 8. That's what 2 squared times 2 is. Still r and s to the 5th. The last thing I can do is some subtraction. And so 2 minus 1 is 1. And that subtraction always results in the numerator if you're doing it what I call directly. So r divided by 8s to the 5th would be our answer there. And let me make that look more like an exponent, which really just means write it smaller. Alright, so we're good there. Again, for that one right there, there are multiple ways to kind of see what you could do with that problem. You could just, I'm trying to think. I mean, you could move that to the bottom in the first step. There'd be some different things to do there. So there's multiple approaches of how you see this. It's just up to you. Also, again, notice that what I'm defaulting to is usually what your homework will do, which they'll say write your answers as positive exponents. All right, number 10, make sure that in your mind mentally that only the 5 is being cubed. Now, also be careful. This isn't transferring to the bottom, because the only time we transfer to the bottom is when the exponent is negative. If there's a negative out front, we're just saying, hey, there's a negative, and 5 cubed is 125. Now this one, especially because there's no variables, would be a great time to just practice plugging it into your calculator. Up next, I guess in order, would be this one. Negative 3 to the 9th power. Really, we'll just have to work that out. And so, 1 minute. I'm going to pull up a calculator so we can see how to type that in. Alright. Sorry, it was the negative 3 to the 9th. So, depending on your calculator, you can usually write in parentheses so that you make sure you have your negative 3. And then if I want to raise that to some power, there's usually this button here somewhere where it'll usually say something like x to the y or a to the b. In other words, saying you have a base and you want to raise it to any power you want. And we wanted to the 9th. And there's my answer, negative 19,683. So on the ones where you only see numbers, there's no variables, there's no R, S's, T's, or B's, definitely practice typing those into your calculator to make sure you get the right answer. But try them without. I mean, this one is just kind of, you gotta work that out slowly. So this next one, though, I think would be one, when the exponents are small enough, I would try them out by hand. So the idea going on here is now there is a minus sign and there is a negative exponent. Now the minus sign, because it's not wrapped in parentheses, is not included in my exponent rule, so there's now going to be a negative 1, and I'm going to transfer that negative exponent to my denominator. Now it's positive. And so, well, that's just negative 1 over 16. And again, use your calculator to verify that result. Okay, last one, a little bit of a challenge question here. Now, there's two ways you can approach this. You can either, and I think we'll do this the real PEMDAS way, we'll clean up our parentheses. That's what the P stands for. It means, hey, if there's stuff that can be combined inside your parentheses, do that first, then deal with any exponents. So I think it'd be a good idea to follow PEMDAS here. So 4 over 3 actually doesn't simplify. That's okay. But a squared minus a to the negative 3 becomes a to the, fifth. So I'm just doing that division rule. I had 2 minus negative 3. Now I have a to the fifth. If I have 7 minus 2, I now have b to the fifth. Every time you do subtraction or this division rule, or quotient rule rather, of exponents, the answer goes in the numerator if you're doing it directly, so to speak. Now that I've cleaned that up, now let's deal with the cubing. And so 4 cubed, careful, is 64. A to the 5th cubed is a to the 15th. They're going to multiply. That means we'll have b to the 15th also. And 3 cubed is 27, and it was on the bottom, so it stays there. All right. So this is a wild section. It is going to take some time to get used to. But once it clicks and once you memorize those rules, especially that negative exponent rule in division, again, think about, I could have just made this a to the positive 3 up top, and now I've got positive 2 and positive 3, and now that's the fifth. I could have, here, I guess I would have done this one as division because they were both positive already. But, again, there's that choice when you see a negative exponent. Am I subtracting a negative, or is it now moved to the top and I'm now adding? That's up to you, and any choice is technically fine. For this next section, we're not going to write down the kind of facts about scientific notation. I think most of us know what it is. I think the one thing I will say, though, is that the number up front, so maybe, sorry, I guess we will. The idea here is the absolute value of A has to be between 1 and 10. And we'll just say if B is positive, you're representing a large number. Okay. Now, the main thing about scientific notation is it turns out one interesting rule happens when you multiply a 10 or divide a 10. All you do is you move the decimal place over 1. So the idea is, and look at these two questions, these two things that are already in scientific notation have an initial value that's between 1 or 10, whether it was positive or negative. Now, the negatives weren't here, but these would still be valid if there was a leading negative, because the absolute value, if you take the negative away, it's still between 1 and 10, so we're good. From there, again, the idea is if B is positive, you're representing a large number. So this is in scientific notation, so what's its real number? What I'm trying to say here is if I see a positive 6, that means I'm moving that decimal place to the right. So 1, 2, 3, 4, 5, 6 places because it was 10 to the 6th. If I then fill in those new gaps I created, I had 3 zeros I had to fill in. So this is 5,403,000. All right. Up next, if I've got 7.0, and this is 10 to the negative fourth, I'm going backwards to the left. 1, 2, 3, 4. And now I've got a 0.0007. Maybe I could put that leading 0. But we moved it left because it was 10 to the negative fourth. We were representing a small number. All right. Now we're going in reverse, so this isn't too bad. The hardest part, I think, in some of these is just how far do I move the decimal? Well, until you get to a number between 1 and 10. So I need to move it 1, 2, 3, 4, 5, 6, 7, 8 places. That's now negative 2.06, and then there's no more digits. And I moved it 8 places. So I could even write that. And then the question is, was this number very large or was it very small? Well, it was very large, so to re-represent this, I would need to move the decimal place back to the right to represent this very large number. So the 8 should stay positive. Okay, last but not least, here's this one. I need to move the decimal place over 1, 2, 3, 4, 5, 6, 7 places. So I know there's going to be a 10 to the some kind of seventh. It might be positive, might be negative. We'll think about that after. Now there's 5.2. And then is this a very large or very small number? Well, it's a very small number. Or again, in other words, to recreate this number, I need to move it left 7 places. So negative 7 as my exponent. That's all there is to it. Now, these questions up next are kind of challenge questions. But the main idea of where these come from is actually way back in the early days of computing, we really didn't have enough bits and bytes to represent very large numbers, and so we had to use scientific notation as a way to store them. Now that technically means you're losing some information because it wouldn't hold on to all the decimal places all the time until we got more RAM and memory, and now we don't even worry about that. But these examples feel kind of silly because you honestly can type all these into your calculator directly. It'd be more interesting if we had something that had like 32 zeros at the end, but that'd be hard to count them all out. But that's more so the ideas. Scientific notation shines when you have to do some very large or deal with very large or very small numbers. And that's when, again, your old computers would have said, I don't have enough space to compute these individually, let alone multiply them and figure out the result after. And so let's see what you could have done with some early computations. So first we're going to re-represent this. Now one nice thing is large numbers have every 3 digits separated by a comma, so I already know that this is 7.5 times 10 to the 9th. And this one, let's see here, is 1, 2, 3, 4, 5. I think, 1, 2, 3, 4, 5 to the left. So 3.1 times 10 to the negative 5th. Now, what's cool about this is since these are multiplying, we can now take advantage and just use a basic calculator with those smaller values. So I can take my 7.5 and multiply my 3.1, which is 23.25. Times 10 to the, and here's where we learned our exponent rules. I've got a 10 to the 9th times a 10 to the negative 5th. Those will combine as is, or in other words, add, but they're adding with a negative, so we end up with 10 to the 4th. Now we're almost done, except that this number produced by the multiplication is now bigger than between 1 and 10. So I need to move the decimal place over one more time. And because I just did that, I now would need an extra positive decimal to get back to where I was. If I move it over, I now get rid of that extra decimal. I'm back to what I had before, but this would be my final answer. So again, not very exciting. I mean, you can technically times 0.1234 leading zeros. You can work that out right there, and you can see that I had to move it 1, 2, 3, 4, 5 places, so I know I got it right. But in the early days, again, your phone, or not even phone calculators, the regular calculators wouldn't be able to handle that many digits. You would get what they call an overflow error, You can still make them sometimes, but you need a much bigger number. So if I had 2 to the 200th, or not even, 2 to the 2000th, now we get an overflow error. So it's still possible to show up, but it happens way less frequently. But we wouldn't want you to count all those zeros to make the scenario meaningful. Anyway, let's do one more. This would be 2.88 times 10 to the 4th. And then on the bottom, I've got 6.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. All right, I need to do that division. So 2.88 divided by 6.4. I get 0.45 that goes in the numerator. So when you do division directly, that answer's in the numerator. And now 10 to the 4th divided by 10 to the 10th is 10 to the negative 6, because when I do division, the result goes in the numerator. Now I'm almost done, but this new number, once again, is now no longer between 1 and 10. So I need to move this an extra place over. I got to think about that for a second. I just moved it to the right, so to reproduce it, it would go back to the left or become smaller. So there we go. And we can confirm that result by, again, just plugging it in. 28800 divided by 6, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 4.5, and actually it just gives me the answer right away because of the way it calculated it. So that was kind of interesting. So really, a lot of those should be nice, easy calculator questions. Well, I already explained the history. Okay, we're going to skip the definitions here, but we're just going to say that monomial is 1 term, binomial is 2 terms, trinomial is 3 terms, polynomial is anything more than 3. And technically, polynomial is the name of all 3 of these. It's just if we see a 1 term, 2 term, or 3 term, we're going to say their specific 1, 2, or 3 prefixes. Anything more, we'll say poly, but technically all of these count as polynomials, just to say out loud. Okay, what do we mean by that? Well, we've got these examples here where they want me to add 2 polynomials. Actually, specifically, if we look at this, they want me to add 2 trinomials. Now, the thing here is the parentheses are written to show what I just said, that you have 2 trinomials. They're each in their own parentheses, but now I want you to add them. Well, the thing about that is, once you decide to add 2 things and you don't do any other operations, you don't actually need parentheses when you do that substitution. So the first step, and I won't do this for the second one because there's no point of really writing it twice, but it's just to say that that is your first step, to realize that parentheses are redundant and this can now be written as 1 line. The issue is, if you just write that without parentheses, you might be wondering, why are they saying adding polynomials? It just looks like I'm combining like terms. Well, there are like terms, but it's because there were 2 separate polynomials. Anyways, just trying to explain why the parentheses are there, to show that there were 2 distinct polynomials, but at the end of the day, it doesn't matter. We are just combining like terms. So, I see a 9x squared, I see a 3x squared, that's 12x squared. I see a negative 7x and a positive 6x, that's negative 1x. I see a negative 5 and a negative 3, that's negative 8, and I'm done. Great. Up next, let's deal with this one. Now again, we're just adding these 2 ugly looking things, so the parentheses are redundant. I have a 2.58 to the 4th and a 1/8 to the 4th, so I have a 3.58 to the 4th. Now you do have a calculator in this class, so you don't need to worry too bad about this, but honestly, we haven't done too much simple subtraction or addition of fractions, so I think we'll work this one out. We have a negative 4/5 AB cubed. We have a positive 1/3 AB cubed. Let's deal with that. Negative 4/5 plus a 1/3, and we don't need to write the AB cubed. We'll write that after we deal with these fractions. When we want to add or subtract fractions, we need to create common denominators. That would happen here by multiplying this by 3/3 and this by 5/5. Now, why are we doing that? In case you don't remember, it's because we are changing the appearance of my fractions, but I'm not changing the worth of my fractions. If I multiply by 3 over 3, 3 over 3 is just 1. If I multiply by 1, I'm not changing the value, but I am changing how it looks. But now they both have a denominator of 15. And so now these two things can go together. So now that I've worked that out, negative 12 and positive 5 is negative 7 over 15 AB cubed. Once, or I guess not once again, but now there's a 2/3, technically plus 1. So that's 2/3 plus 3/3. Well, that's 5/3 AB. And then there's negative 6 and negative 1, and that makes negative 7. All right. Now, there's not much more to it except when you're subtracting, and there's even the hint there, we're going to distribute and combine like terms. And once again, the parentheses are here to say, hey, here was polynomial 1. This time it's a true polynomial. There's more than 3 terms. And here's polynomial 2, something else that has 3 terms, or more than 3 terms. Now we're subtracting them. Now normally that wouldn't matter, but we do need to write it out this time, because when you subtract something with multiple terms, you are distributing that negative. And so it's not just negative 7u to the fourth and keep writing. No, it's negative 7u to the fourth, and now it's double negative positive 5u squared. Now it's double negative positive u, and it's negative times a positive negative 4. That negative just switched the sign of every term in the second polynomial, because that negative is multiplying and distributing to every term of that second polynomial. And so from there, 6 and negative 7 is, well, negative 1. Negative 1 and positive 5 is positive 4. Negative 12 and positive 1 is negative 11. And negative 8 and negative 4 is negative 12. So after you do that distribution, it's really, really easy. It's just combining like terms. Now this last example I want to go over specifically because I think there are some non-like terms, and I just want to show you what happens there. So unfortunately, because we're subtracting, I do need to write each one of these out. Whoops, that was squared. So now it's minus 1.5 x to the fifth, but don't stop there. It's now minus x cubed y squared. It's now positive 2xy squared. It's now negative 4y. And it's now positive 1.3. All right. So we just finished negating or changing the terms of every part of the second polynomial. Let's get combining. And notice that we have 2 of these polynomials, so we can kind of see our order here. It looks like the x to the fifth goes first in both. So a positive 0.6 and a negative 1.5 will be negative 0.9 x to the fifth. You can, if you want, cross them out as you go, but you might not want to cross them out too intensely in case you need to go back and read and check your work. Now up next, they both have the 2xy squareds in some way, shape, or form, but I also see this x cubed y squared going next in this one, so let's take care of that. Well, this one doesn't have a buddy over here, so what do? Well, don't worry about it, you just recopy that one. If it doesn't have a buddy, it just gets copied and follows along. Now next, our next term is the negative 2y squared, and because of the negating, I have a positive 2xy squared, and that's just going to cancel out entirely. So I now use that. The positive y and the negative 4y is negative 3y, and negative 1.5 and positive 1.3 is negative 0.2. All right, we're done. Up next, we're really not going to go through this whole one, but I just want to show you what this is saying. This is just a shorthand of saying this is x squared minus 3x plus 5 plus x squared minus 2x minus 9. And I guess we'll work that one out quickly. That's going to be 2x squared. That's going to be minus 5x minus 4. Because that was addition, it was really easy. Part B, though, again, it's the same thing, but just realize this is a shorthand way of saying copy the first one, but now write your minus sign, and now the parentheses really do matter because you are going to have to distribute. And there you go. Now I'm going to work that one out actually because it's interesting. X squared minus x squared disappears. A negative 3 and a positive 2 makes a negative 1. I know I'm working that out a little quick, but again, this is kind of a recap, hopefully. And there we go. Now, the thing to point out about that is maybe just to say out loud that just because you have a 3-term polynomial and a 3-term polynomial, or rather if you have a trinomial and a trinomial, you might get something different if you add or subtract them, so just be careful of that. Now, last one here is just saying, hey, take h and take k, evaluate them at negative 2 and add their answers. Now, there's actually two ways of doing that. Because you figured out this general h plus k function, so to speak, you could just plug negative 2 in here and get your answer. Or you could plug in negative 2 back into the original and solve, and plug in negative 2 back into the original and solve, and then add those two results. Either one will work, but we'll skip that for now. Alright, on to one of the more important sections that we're going to cover is the multiplying polynomials. The good news, or hopefully the good news, is that this should be a familiar concept, and it should feel like something you did in some of your prior math classes, or hopefully did a lot of, and you'll recall it. So let's go ahead and jump in. Alright, so here we go. We're just doing the distributive property. So 2x cubed times 7x squared would be 14, and then using the rules we learned, x to the 5th. Because 2 cubed is multiplying, x cubed is multiplying x squared, so they add. Up next, 2 times negative 1 is negative 2. X cubed times x to the 1st, there's an invisible 1 there, would be x to the 4th. And finally, 2 times 4 is 8. And maybe to say it this way to help us for later, x cubed times x to the 0, because there is no x, would still just be 3 x's. And that's it. That's all we're doing, but of course we're going to ramp it up a little bit. So let's see some uglier examples. And we just deal with this term by term, and we also deal with it variable by variable, or I guess part by part of each term. So first the coefficients, negative 4 to 6 is negative 24. And now our x's, 1x, 3x, that's now 4 x's. Y squared, with no other y's, would still be y squared. And a z makes z squared. Alright, so that was negative 4x y squared z to the first term, and we just keep going to all the other terms. Negative 4, negative 5 is positive 20. X to no other x's is just an x. Y squared to a y is y cubed. And z to z squared is z cubed. Last but not least, negative 4 to 9 is negative 36. X to x is x squared. There was a y squared and no other y's. And there's a z to z, which is z squared. And we're done. That's all there is to it. So, the thing to say early on, just to hopefully not scare you, but let you know where we're going, is what we're about to do in chapter 6 is how to figure out how to see this the opposite way. So, how to see 14x to the 5th, negative 2x to the 4th, and 8x cubed, and realize, oh, each one of those coefficients shares a 2, and each one of these exponents have at least an x cubed in them that we could factor out. We're going to learn how to go the opposite direction. But for now, we're just learning how to multiply. Well, what's going to be harder in chapter 6, hint to what we're going to be learning, is what do you do when the thing you can factor out has more than one term? That's not too bad when we are doing the multiplying, but it's kind of hard to learn how to factor those out, so to speak. But for now, we're going to use an acronym we call FOIL, which stands for first, outer, inner, last. And here's what that means. It means you multiply the first two things on the inside, which is 30y squared. You multiply the outer two things, which would be negative 35y. You multiply the two innermost things, which would be negative 12y. And you multiply the last two from each parentheses, which is positive 14. Now, this is not a fun way to say it. It doesn't roll off the tongue as nicely as FOIL. And let me combine my like terms as I say this. But really what we're doing here in this example is, I think a great way to say it is multi-term distribution. See, in the first example, we were doing a monomial, single term, distributing to however many terms I have. And here I've got a binomial. That's the main thing, is on the left-hand side, there's a binomial multiplying. It doesn't matter what's on the other side, but once there's more than one term, you can't just go 1, 2, 3, done. You have to say, take my first term of my two-term structure, distribute it to everything else everywhere, and then take my second term, or in this case my last term, and distribute it to each one of those terms. So we're doing, if you want to say it this way, which again is technically correct, but this is why we came up with FOIL, but you're really just doing multi-term distribution. If you can see it that way, maybe it almost makes it easier. So up next, I take my first term, distribute it to the other first term. That's the f of FOIL, but I'm really just doing multi-term distribution. I now get t to the fourth. Now multiply it to the other part. I'm still on that first term. I'm multiplying that first term. That'll be a 4, and let's think about the alphabet, TUV. So T goes first, so we'll put that first, then the U. Up next, the inner, or again, since I applied everything from the first term to everything in the other set of parentheses, it's now time to move on to the next term in the sequence. So now negative U multiplying to 5t squared, or the inner of FOIL, is, well, negative 1 and 5 is negative 5. Going in alphabetical order, there's still a t squared, and there's just a u. So I can reorder those because they're all just multiplying together. And finally, there's a negative u squared. Now, because I reordered them alphabetically, it's clear to see that there are still some like terms from my multi-term distribution, or from my foiling. There's a negative 1 t squared u now in the middle, and the negative u squared at the end. All right. So, the thing, again, just warning early on, is you can kind of see that it's pretty difficult to figure out where on earth are the 4 and the 5 and the U coming from to make this whole thing. I mean, you can kind of see the 4 and 5 and the 20, but you know, this one, the 30 and 47 and 14, where are those numbers coming from? It can be a little tricky to guess what they are, because there's many different options for 30. There's 3 and 10, 2 and 15, 1 and 30. How did we end up with a 5y and 6y? You know, just leading on to, it's kind of amazing that we can take this 3-term thing and figure out, oh, it's actually a product of these two smaller expressions. And by smaller, I mean lower degree, right? So anyways, let's keep on moving on. The now thing to worry about, and this was the warning, is that now I see a squared, and I cannot just put that squared to the 3y and the 1 and move on. And you might be saying, but whoa, we did that earlier today, or in this video, depending on how you watched it. And you're probably referring to number 3 on the first page, where there was this set of parentheses squared, and I did just take that squared and moved it to the 4, the x, and the y, and moved on. Here's why I did that, though, and if you rewind it back, I did make a note, is that this is all one term. There's no addition or minus sign between here. So I can get away with, so to speak, just applying that 2 to each part of this single term thing being raised to a power. Once there are multiple terms, you cannot get away with just exploiting that exponent rule. You're going to have to actually use what exponents mean, and you could do this on that other example 3 to practice and see why it works, but you're going to have to first say, my first step is actually not being a lazy mathematician and writing this thing out entirely twice, because after all, that's what that exponent of 2 means. Now that I've written it out twice, well, this is no different than any other example. So it presents itself differently, but you're doing the same work. You just need to realize step 1 is actually listed out twice because there are multiple terms. I can't just put that 2 to these two things. You'll see why as we FOIL, because if you thought you could, and I'll just say it, I won't write it, you would have gotten 9y cubed and just a 1. Let's see what happens when we FOIL. We do get a 9y cubed. Oops, sorry, squared. I said cubed, I meant squared. I was thinking about 3's. Then I get a 3y. Then I get a 3y. And see, those weren't in what I said before. And then I get a 1. And when I combine all that, I get a 9y squared. I get a plus 6y and a plus 1. So from the foiling process, from truly writing this out twice and doing my multi-term distribution, I realized that it's not just 9y squared and not just plus 1, but there's a middle term that presents itself because of the way that the exponents play off each other as I go through my foiling or my multi-term distribution. Okay, let's just keep going then. Again, step 1 is realizing we can't be lazy. We have to write this out twice. And so 4 to 4 is 16. I've got a negative 4n cubed. I've got another negative 4n cubed. And I've got a positive n to the 6th because my bases are multiplying, so my exponents are adding. If I combine those and reorder them, why not? I get n to the 6th, negative 8n cubed, plus 16. Usually we write our final answers, or we rewrite our polynomials from highest degree to lowest degree if we can. Alright, now the next example is kind of special. Maybe you can see why, because it almost looks like the same thing twice, but there's just one sign switched in between. So let's see what happens now. I get 9y times 9y, which is 81y squared. I get a positive 18y. I get a negative 18y, negative 18y. And a minus 4. If I work that out, that's 81y squared, but those middle terms completely cancel and I'm just left with negative 4. Now this is really, really interesting because finally, or especially, when I did my foiling, I didn't end up with 3 terms, I ended up with 2, and they were subtracting in between. When does that happen? When you have something we call conjugates. Conjugates are when you have a plus b and a minus b. In other words, you have the same 2-term binomial, but the sign in between is switched. So examples would be, well, what we just saw. So we could say x minus 2, x plus 2. Those would be conjugate pairs. But for another example, negative 3x plus 5 and negative 3x minus 5. Those are conjugate pairs as well. And people usually look at this example and they stop and pause and go, wait, those aren't conjugates. You only flipped one of the signs. But yes, I did only flip one of the signs, because what this definition is saying is only the sign in between the two switches. See, if the a was positive, it stayed positive. If the x was positive, it stayed positive. But if my negative 3x is what starts, then negative 3x is what still starts. It's just the sign in between that switches. And the most important thing about conjugate pairs is this behavior. Look at what you get after you FOIL out conjugate pairs. You get, we have a name for it, differences of squares. See, 81's a square, y is a square, and 4 is also a square. So when you FOIL conjugate pairs, when you FOIL conjugate pairs, you get a difference of squares. And guess what? The opposite is true. If you have a difference of squares, it comes from conjugate pairs. So we just wanted to find those early on. Okay, up next, I want to do this one example, not necessarily this part B, but I do want to show you why I refer to this as multi-term distribution and not foiling. Because sometimes things like this happen, where they want you to multiply maybe a binomial to a trinomial. And now the word FOIL doesn't work because you're not going to have a first, outer, inner, last, because you're going to do multi-term distribution. I'm going to take term 1 from the left-hand side and put it to all terms on the right-hand side. So now I have negative 18 x squared, and I have 3x times 2 is plus 6x. All right, and so now I've used the first term with all 3 parts of the right term. Now I need to do the same thing with the next term. And so you could imagine if this was a 4 term to like a 5 term, there would be a lot of kind of these little arcs you'd be writing. and it'd be hard to keep up with it all. So one tip to keep up with it all is if I now have negative 5x squared, think about where you write, and don't just write a solid line all the way across. Go, wait a minute, I already saw an x squared, so let me stack those underneath. Let me already start stacking my like terms so I can see them combine easier, if you notice that they'll end up being like terms. Up next, negative 5 to negative 6 will be positive 30x, and I've already seen a single x term. And then I see a negative 5 to a 2, which will be negative 10. I've never seen just a number without a variable, so that goes on the end. So I combine, which would be negative 23x squared, which would be plus 36x and minus 10. And now I'm done. Great. So it is possible to deal with more than two terms to two terms, and that's why we don't like the term foiling, because it really is just that special case when it's a binomial to a binomial. If it's not a binomial to a binomial, then that's where foiling no longer works as a phrase to tell you what to do, but really multi-term distribution. Think about it that way. Term 1 of this left side distributes everywhere. Term 2 of this left side distributed everywhere. There were only two terms, so I'm done. If there was a third, term 3 would have distributed everywhere, so on and so forth. All right, last but not least, 5.4, just 3 quick examples. We can do it. So we're now just dealing with, or almost introducing the idea of what are we going to be seeing in the next section, honestly, is how I would describe this. So, in other words, we're going to start to say, hey, what if all these 3 things shared something? Could I divide it out? And maybe someone already identified that 6x cubed is what's shared, or maybe there's something more, but that's the idea. Is what would it be like to take each one of these terms and divide a 6x cubed? Because that's what you need to realize. This is a shorthand for mathematicians are lazy, remember? So it means this is really what you have. Each one of those terms is over that 6x cubed. And so we're going to do 3 little problems of what we learned how to do. So 54 divided by 6 is 9. X to the 5th divided by or minus x to the 3rd would be x squared, and it would be in the numerator because I did subtraction directly. 42 divided by 6 is 7. 4 minus 3 is 1 in the numerator because I did it directly. Negative 24 over 6 is negative 4. 3 minus 3 is 0, so I don't need to write next anymore, and I'm done. Awesome. So let's keep on going. We don't need to write this out as true division every time, but just realizing this is an equivalent way of writing what we just did up here. So 12 divided by 4 is 3. A2 divided by A2 would be no more A's. A to the 5th divided by a single B would be, B to the 5th divided by a single B would be B to the 4th. So that's what's left over. Negative 20 divided by 4 is negative 5. A to the 4th and A squared will make A squared. B minus B, or B to the 1st minus B to the 1st, or 1 minus 1 is 0, so no more B's. Finally, 6 divided by 4 is, 3 over 2. But that's okay, we can write a fraction. A squared divided by A squared is nothing, and there's a B left over, and it's actually left over on the bottom because this time there was no B on the top to cancel out. So that can happen, where you still end up with a fraction as your answer if there was no pair in the numerator to work out with. All right, one last example, but honestly, I'm not too worried about it, and we'll see this more in the next section, so we'll just skip that one for now. There's our Chapter 5 guide. All right, I'll see you for Chapter 6.